Good morning, everybody in the lecture hall. Good morning, everybody on Zoom. Good morning, everybody from the future, binge watching us for the exam. So where are we? So you remember the whole thing, what we did during the semester. We first looked at how to store data. We then looked at higher levels with validation, processing, and so on. We also saw that there are plenty of shapes of data. Table is the most popular ever, thousands of years old, and for this, the technology stack, it's quite mature. We even saw that we found tables again with HBase, and then we found tables again with Spark, which is a special case of data frames, even though, of course, data frames can do more than tables. They can also allow for nestedness. And now it's time to look at something different, this time a fully integrated product. And as a reminder, what characterizes trees as opposed to tables is two things. The first thing is the nestedness. You can have multiple levels of deeper data. It's like a table in a table in a table. But now you know that when we say a table in a table, we are really talking about an array of objects inside an array of objects inside an array of objects, right? So an array of objects, if the objects are all valid and against the same schema, and if they are flat, then it's basically a table. So this is the nestedness one. The second one is heterogeneity, and heterogeneity is if you drop the schema. If you don't have any schema, then the objects you would have in an array can all look different, and the objects that you could have in a collection on the outer level could also be completely different, right? So that's the beautiful world of NoSQL, not only SQL, these two things. So we need an equivalent of PostgreSQL for this, right? So in this kind of data store, we actually call it a data store. I will explain why we don't call it a database management system or like a data store. We have collections of trees, right? Just like we have tables in PostgreSQL, in MongoDB, in document stores, we have collections of trees. And we saw last time that we are talking about millions, billions, trillions of trees, but the size of the tree is limited, right? So you can go all the way to maybe 10 megabytes, 16 megabytes, but not more than that. So many systems actually restrict, like MongoDB doesn't even allow more than 16 megabytes. Other systems will not forbid it, but things can start being slow and go wrong if you have too big objects, right? So a huge collection of, let's say, medium objects, right? I'm not going to say small because small would be like a cell in a relational table, or a record, but here they can actually be medium. For whom is that clear? All right. So again, what it means, this nestedness and heterogeneity, is that we can take a collection of trees and we can recover tables as a special case when the trees are flat, meaning that we don't have arrays of objects. All the values in the top level object are just atomic values. So in that case, it looks like the record of a relational table, right? It's all flat, just like what you have on the right, as opposed to nestedness in a tree. And the second one is the homogeneity, because if it's homogeneous and all the records, the flat trees, they all have exactly the same types associated with every key and exactly the same keys in every record, like on the left here, then you recover a relational table. So who understands that a table is a homogeneous collection of flat trees? Who sees that? If you don't yet, then think about it, right? A table is a homogeneous collection of flat trees, so it's a special case. And if we look at collections of trees, then we look at something bigger, more generic than just tables. And we saw that data frames are kind of in between, because in data frames, you allow nestedness, but you don't allow for heterogeneity, right? So data frames are in the middle. Data frames are homogeneous collections of possibly nested trees. Okay, and by homogeneous, we mean with a schema. We can validate against the schema. All right. Now, this is where we stopped last time, that in a document store, typically we can kind of retrieve the components of the relational algebra, right? Kind of the same things we like to do with relational tables, projection, selection, aggregation, sorting. We can also do it with collections of trees, and we will see how shortly. There are other things that we like to do with relational tables, and these are joins, but with document stores, it's a bit less popular. We don't join so much. And the reason we don't join is really that, as we saw, trees are denormalized. And we saw that if you denormalize the data, then you don't need to join anymore, because denormalizing the data is kind of like pre-computing a join, right? You already put in a nested way the second table into the first one. When you have the arrays of objects, that's kind of a pre-computed join. So this is why joins are a bit less popular. It doesn't mean that they don't exist. Of course, you can still have them, but many products, including MongoDB, do not even bother to give you an API to do the joins. It doesn't mean you cannot do them, but if you want to do them, you have to program them yourself. So you have to use Python, C++, whatever language you want, and you have to implement the join algorithm. Okay, so this is why I marked it as a no here. It's really projection, selection, aggregation. Then, because I mentioned heterogeneity, in PostgreSQL, you need a schema. If you don't have a schema, you cannot even put data in your table. That's the first thing you need to do in PostgreSQL is define the schema of the table, but not in MongoDB. In MongoDB, document stores, you can just pour the trees into your collection without a schema, and it will just work, even if the trees are heterogeneous. But if you do want a schema, you can. It has the flexibility. So you can either define a schema from the very beginning and then only allow the documents that fit the schema and throw an error if they don't, or you can do it the reverse way. You can first pour the trees in your collection, then maybe clean it up, and then validate against the schema and then force the validation forever. Or like if you add new trees, it will have to be valid against the schema. So we have more flexibility because we are not obligated to validate at the beginning. We can do it later, right? But of course, the challenge, and that many machine learning engineers know, or data scientists, is the cleanup of the data. How do we clean up the data, right? Because once it's normalized, that's it. Once it's clean and you can even put it in tables, then the job is done. But the challenge is really what about the data that's heterogeneous and nested? How do we manipulate it with the goal of cleaning it up very often? Okay, so when I say document store, and I already said MongoDB once in a while already, there's a whole ecosystem of them, many, many, many. MongoDB is one of the most popular ones. MarkLogic is one of the most enterprise-ready ones, at least back then. Probably now a lot made progress. Some are JSON, some are XML. It's easy to see those who have an X in the name is probably XML, and those who don't is probably JSON, right? So you have CouchDB is JSON, MongoDB is JSON, Elasticsearch is JSON, even though Elasticsearch is more for indexing the data. Cloudant is JSON, MarkLogic kind of everything, even graphs. I mean, it's really, Microsoft Azure has Cosmos DB, I think, that also kind of does everything. BaseX, then that's XML because of the X. ExisDB is also XML because of the X. But really, it works the same way. It's pretty much the same thing. Even the languages, the way that the languages work are quite similar, even though the level of the languages might differ, but I'll come back to that. Okay. But in that course, I'm going to focus on MongoDB, right? And you will see if you want to learn any other, it will be easy, right? Because again, these are the principles that we'll cover. All right. So MongoDB it is. So let's start on the logical level. How do we query the data in MongoDB? So what I already told you is that MongoDB stores collections of trees. And I already told you probably a few weeks ago that we distinguish between two approaches to the way we store data. There is on the one hand, the good old database management systems, where we have to first import the data before we can do anything with it. That's the case with PostgreSQL, right? If you use PostgreSQL, you have to first populate the tables before you can query them. But in that case, the way the data is stored is hidden from you. It's whatever the system wants to do with it. It has ways of optimizing the whole thing on disk. You will never get to see the physical layout of the data on the disk, except maybe advanced people who are interested in this, but you don't. ETL means extract, transform, load is just a synonym for import, right? And it's a verb. You can actually say I ETL, you ETL, he ETLs, she ETLs, and so on, right? Okay, and on the right, we have data lakes, and data lakes have become kind of a buzzword. In that case, you don't import the data. You just copy it over on object storage or into a file system. In fact, this is what we did with S3, with HDFS, with Azure Blob Storage, Google Cloud, and so on, right? All of these are data lakes. Even HBase could kind of be considered some sort of data lakes, even though it's bidimensional rather than flat. Okay, and so for weeks, when we studied MapReduce, when we studied Spark and so on, we kind of looked at data lakes. And again, what characterizes a data lake is that you can see the data, you can see the files, you can see the JSON, you can see the XML, it's all there, the CSV, these are actual files you can look at. But today, we are going to deviate from that. We are really going to look at a system where you import the data first and you don't get to see the physical layout of the data. You won't see any JSON files, you won't see any XML files. You will just see a logical model of JSON or XML. And again, put it in perspective with PostgreSQL, right? In PostgreSQL, it's for tables, MongoDB is for trees. So far, so good, everybody with me? Okay. Now, I have only just one slide. I don't want to scare you, but just to have said it. I told you that since it's a system from the left where you import the data first, MongoDB gets to store the data on disk in any way it wants, hidden from you in a physical layer. And in fact, it so happens that MongoDB uses a standard called BSON, which kind of means binary JSON. It's kind of an improved JSON that is more compact. So now you might think, okay, yes, but why not Parquet? But you remember that Parquet requires valid data. If the data is not valid, doesn't have a schema, you cannot use Parquet. So BSON is kind of in between. It doesn't require a schema, but at the same time, it's a bit more compressed, takes less space than the text JSON file, right? If you would have an actual JSON file. You don't even need to know how that works. It's just a mapping from the syntax of JSON to some binary data. What you see here is just the base 16, which is just a shorthand for zeros and ones, right? Okay, so it's just called BSON, right? And there's a link for those interested. It's not part of the material, but for the curious, there is a website. I think it's called bsonspec.org or something like that, where you can see. Again, I didn't want to scare you. I just wanted to mention it, but you don't have to know BSON, just that it exists. All right, now if we want to query the data, as we will see, it doesn't have the same glossy finish as PostgreSQL, also known as SQL. It's slightly more on a low level, the way that we interact with MongoDB. But don't worry, we'll add back a language like SQL shortly. Maybe even we'll start with it. Actually, it's JSONic, so you already saw it. So MongoDB has a low-level API. It means that it's not really a language, because in fact, the language would be JavaScript or Python or whatever language you want, but it's really an API within a language, right? So it's a bit on a low level, and I'm going to show you a little bit how it works. But again, a word of warning, again, it's not the same finish as having a language like SQL. When you have a low level like that, the paradigm is called CRUD, create, read, update, delete. Right? In fact, in HBase, it kind of sounds like get, put, scan, delete, right? It's a little bit this short list of primitives. So let's go through them. So here I have a few slides with examples. I mentioned the language can be Python, can be JavaScript, so there's many ways you can access it, but the most popular one is JavaScript, so I'm going to be using it. But don't worry, it doesn't mean that you need to learn JavaScript, because in fact, we focus on the API here. And there's also an API in Python, there's a few differences. But since most people, when they learn MongoDB, they use the JavaScript API, we'll focus on that one. All right. So here's the thing. I'm going to have in the middle of the screen, this DB scientist find blah, blah, blah. That's how I query the data using the MongoDB API in JavaScript. Would be similar in Python. Here, I put the results. What is output? Here, I have a cheat sheet where I put some SQL equivalents, right? It's approximative, right? It's just to give you an idea of the corresponding SQL command. It will not always exist, of course, because that's more powerful in terms of, because we have trees, but just so that you see the point. So this select star from a table returns everything, right? So how do we do the equivalent? Well, we just say DB, it's always DB, dot the name of the collection, so scientists that would be put in here. Then we have this find method that you apply in the name of the collection. And then you can either pass nothing or an empty object, doesn't really matter. And then you get everything. So here, this is my whole collection. Of course, I don't have room for millions or billions of objects on my slide, so I just put the objects right here. Also, to not scare you, I omitted a special primary key that's called underscore ID, that is just some sort of a number in base 16. All objects have that. It's automatically added by MongoDB to make them unique, but I'm not going to overload my slides with that, right? So just so that it looks like a relational table, I just have put it like this, right? Who sees that this actually looks like a relational table in that case, right? It has a column first, a column last, and a column theory, and these are all strings. Okay. And I mentioned the ID field right here, but again, I don't want to overload my slides. All right, so this is the select star from. Now, what if we want to select something, not just star, but with a criterion? Well, in SQL, we do it with a where clause. So here we have where theory equals relativity. But again, MongoDB doesn't support SQL. In MongoDB, we would have to put what we want to filter with, the selection predicate, inside the objects that we feed into the find method. And now you see it looks like JSON, but of course it's JavaScript, right? So you can actually put JSON in JavaScript. And here, what you're saying, it's like this API says, I want to have the object such that theory is equal to relativity. We have a question, I think, on Zoom.
So how does it handle if the JSON already have an ID field?
In that case, it just takes it. If you put some JSON in there that already have an underscore ID field, it's going to take it over, right? I can't remember if it would complain if the value of that underscore ID is not this base 16 string called an object ID. That I cannot tell you. We can check offline. But if you do put an underscore ID field and the value is correct, then for sure it's going to take it over. And if you don't, it's just going to make up one for you randomly, right? No, it has to be unique. That I forgot to mention, right? It has to be unique. So if you try to insert a new one, then there's two strategies. I don't know exactly for MongoDB. Either you can throw an error by saying, no, it already exists, or you can just replace it, right? And then maybe different products are going to do it differently, but it has to be unique. This is a primary key, this underscore ID, okay? All right. So that's how we do a selection, and we feed that criterion as a JSON object inside the find function. Okay, and you see we return the first and the fourth object in that case, but not the second one and the third one, because the value of theory doesn't fit relativity. Who is with me? Okay. Now, we can also project. Projection is due with a second parameter to the find method, where we specify the fields that we want to project to associated with the value 1. So if we say first one, last one, then we just project to first and last, and now theory is disappearing, right? For whom is that clear? Okay. And now is probably the moment where you start feeling uneasy and like, what is that syntax? Like first one, last one, second object, and so on. Like compared with SQL, it's more complex, right? But again, I warned you, that's not a language, it's an API, right? And I'll show you a language that manipulates NoSQL a bit later. So it's an API. Okay, now we can also have a 0 in here. In fact, that's the reason they put a 1 in here. You can also have a 0. 0 means projecting away. Now that's something we didn't have in SQL. Projecting away means I want everything except this attribute and that attribute. This is called projecting away. So in that case, when you say theory 0, you're just asking for everything except theory, right? I'm not talking about the underscore ID that behaves a bit strangely. So I think you're not technically removing underscore ID. You can remove it explicitly. But even if you project on first and last, it might still include the underscore ID in that case. But again, I didn't want to bother you with the underscore ID thing. So let's just forget about the underscore ID. All right. So projecting and projecting away. Then how do we have the equivalent of an AND? What if you have multiple predicates? Well, if you are just looking at the values of different attributes and want to, for all of them to be fulfilled, then you just put them inside your first object, right? So the first object is for the selection. The second one is for the projection. So if you put in your first object more keys than just one, then you have the equivalent of an AND right here. And now you would only select this one because it's the only one that fulfills both of my criteria, right? So this is an AND. An OR, please be seated, don't be scared. This is an OR. And here you see again, it's not a language, it's an API. So the way you do it is with a special key. They start with a dollar, these special keys, and you have $OR, and then you have an array with all the possibilities that you want to allow. So either last Newton or last Einstein, okay? And now you probably start seeing that for simple queries, it kind of works, but you can imagine that for the more complex queries, it might be simple in SQL, but in the API, that might actually start requiring work, right? So just so that you see the limits of that, right? It's easy to use on simple use cases, but then if it becomes more complex, that might be a bit more complicated, okay? So this is the AND, this is the OR. And now you might ask, okay, what happens if we actually have a key that's called $OR? Well, this is when things start breaking, right? So it would then start causing issues if you actually have dollar in the keys of the objects, right? So some products might provide a way to escape then in some way to say, I don't really mean $OR as the OR of a selection. I really mean $OR as the actual key. Some systems would allow you to do this. Okay. What do we have other than that? Well, we also have comparison operators, right? So in SQL, it's easy. You just write larger than and so on. But since we are using this JavaScript API, we can not just put the same sign in this way. So what we do is, again, use this dollar thing. So we say that publications, and we put an object in there. That means greater than or equal, GTE, to 100. You also have LTE and EQ and so on, right? So you have plenty of combinations. All right, and now we get the publications that are more than 100. So we have Einstein and Gödel, right? Who is with me? Okay, very good. Who finds SQL easier? Okay, so do I. But again, I'll come back to an equivalent of SQL for querying nested data. All right, now what about heterogeneity? Because that's kind of what MongoDB does in the comparison to PostgreSQL. Well, in MongoDB, the collections could have missing fields, could have extra fields and so on. And if you select, it's kind of working naturally, right? Even in a heterogeneous collection, if you say theory relativity, it's going to pick those who have it. It doesn't matter if the attributes, the other attributes are different or not. If it's missing, that's not a problem. You're not going to get an error. It's just not going to return it, right? And if you do want to return it, I don't know if I have a slide for that. You just say, oh, I do. You just say null. So if you say null, then you're looking for either the null value or the absent value. So it also will return the last object. So you specifically asking for null, so it returns only the last object. Parenthesis. The behavior of null versus absent depends on the system. The most general way is to distinguish between them, and that's the way we did it. It's not the same to say that a key is absent or that a key is associated with null, right? When I taught it to you, I taught it to you that way. And many systems do the distinction. MongoDB doesn't. MongoDB says null is the same as absent, right? So just keep it in mind that system dependent, but now you know all you need to do is look at the documentation of the system you're using, and then you know if it considers null and absent to be the same or not the same. Okay, but here it's the same, so the null is actually going to match also with an absent value, and it would also match if it's a null, because it's the same. Okay, in SQL, you would say where theory is null. But again, this is because even though relational tables are homogeneous, you still have kind of sort of a bit of heterogeneity because you can have null in a relational tables, right? But that's about it. You could not have an extra field or anything. Okay. Now, what about nestedness? And now this is where SQL doesn't help anymore, except if you have Spark SQL, then you would have known the dots, right? But the early versions of SQL don't have that. This query here says name.first equals Albert. Now, the first thing I'm going to tell you is the dot is a special character, just like the dollar. So we are not looking at a key that's called name.first. We are really looking at first inside name. So this is going to return the first and the second one, where you do have first Albert inside a key called name, associated with a key called name, and another one that's also an object with first Albert inside a key called name. The other one has name first that would be Kurt, so that's not returned. Who is with me? Okay, so the dot, just like the dollar, is special. Now, a common mistake that many people do is this. They think they would write the query in this way, thinking that they are looking for documents where you have a first Albert inside name. But the thing is, if you do that, it's looking for an exact match of the object. It means that the exact match is only the one in the middle, where name is exactly that object like this. It's not going to return that one. So that's also a common mistake, right? And now you probably start piling up and piling up and piling up all of these conventions of the API, and it's going to be different for every document store, right? But that's how it is, right? It gives you an idea of how things work. All right. Now, there's also a special behavior if we have, let's say, arrays of strings, and in your query, you say theory is special relativity. It's not only going to return those that actually have the string special relativity, it also is going to return those that are an array, one member of which is special relativity. Okay. Another thing you can do is that's the $in operator. You can ask for a value that is one of several values. So if you look at universities, ETH Zurich or EPFL, you can do it in this way. It's $in ETH Zurich or EPFL. So it's going to return the first one, not the second one. Now, it would be the same, this query right here would be the same as an as an or, $or university ETH Zurich or university EPFL, right? In that case, you could also write it as a $or. Okay. Nin would be not in, so in that case, you're doing the opposite, and so on. There are many, many, many other operators documented in MongoDB. They start with $, and you look at the documentation. So that's for the find function. We can select, we can project. What else can we do? We can count. We can count the number of documents that would be returned by a query, and here we do it with an additional method call here, .count, that's going to tell us how many objects pass that filter. Okay, for whom is that clear? All right. What else do we have? We have a way to sort. Again, you need to call a sort method, and you pass an object with keys that you want to sort by. You say 1 for ascending and -1 for descending. That would be the equivalent in SQL of order by founded desk, right? Who is with me? Right. Again, please abstract away from the fact that a lot of the conventions that I told you, like the 0 and the 1 in the projection, the $operator, the behavior of the dot, sort, and so on, it's all arbitrary and specific to MongoDB. So I do share the fact that you have to learn it by heart or look it up in the documentation. That's one of the weaknesses of doing it in this way, right? So, but I wanted to see what an API looks like, right? Okay. Now you also have, remember in SQL, you have offset and limit. You remember offset and limit in SQL? It's a great way to limit the size of the output. If you don't want to crash your Jupyter notebook, add a limit 10 at the end of your SQL query. Well, you can do it here with skip 30, limit 10. It means that you skip the first 30 and you output between 31 and 40, right? Now we have distinct. So distinct outputs all the distinct values of last, right? And finally, and that's the last one I'm throwing at you, we have a very mighty and powerful method called aggregate that does things like first it filters on century 20, then it groups by year and does a count over a sum over the count, then it sorts by the count field decreasing, then limit 5 and so on. Now that looks scary, right? Doesn't that remind you of something though in the structure that we've already covered? That's the reason that's the only slide for that. Doesn't that ring a bell on the way that it looks? Who sees that it looks like a sequence of transformations? Where have we seen sequences of transformations? Anybody on Zoom? Maybe you are less shy to answer. Where did we see transformations, sequences of transformations on data sets? Yes, in Spark, exactly. So this is why I'm not showing to you anything else, because this is kind of a mini Spark in MongoDB. You can also supply transformations. Now, I'm aware it requires looking at the documentation, learning yet another language, and so on. But it's the idea that I want you to see. It has a mini Spark. The way it works with the transformation is the same thing we covered in Spark. It's just a different lipstick, a different finish, but it's basically the same idea. Right, so this is technically, you see creation, transformation stages, and so on. It's the same thing. Okay. Now, how do we insert data? Where we have functions for that, where you can insert, it's like in SQL, like insert into the tables, right? So here you insert one object. You also have insert many, update many, if you want to update multiple objects and set the century to 20, yet another thing to learn. Update one also exists. Then you have delete many, delete one in order to delete and so on. Okay, but I have good news for you, because you won't have to actually program MongoDB at the exam. Who is relieved of that? Who feels relieved? Okay, you don't have to program in MongoDB. The exam is going to be PostgreSQL, SQL. It's going to be a PySpark that you've covered, Spark SQL, or the data frame transformations if you prefer, but Spark SQL is probably easier, and JSONic that you've already seen in the tutorial. These are the 4. The rest is theoretical questions. So we might ask you a few questions on the syntax of how to query MongoDB, but you won't have to write any queries yourself, right? So just to be clear, to make sure that you don't feel overwhelmed looking at all of this, right? I just want to understand the idea, the look and feel, and the limitations of an API like this, and the difference between an API and a language. Because again, we're looking at JavaScript with a MongoDB API. It's not a query language. Okay. Now I can go back to the physical layer, say a few details quickly. Do you remember that in HBase, I told you the atomicity of updates is at the row level? Who remembers that in HBase? Who doesn't remember that? So, okay, let me explain again what it means. It means that if 2 users, Alice and Bob, are trying to update the same row in HBase, they won't be able to do that. They have to queue. So whoever is there first will do an update. The other one has to wait and can only do the update after the first one is finished. So there is a queue. Many systems have this notion of queue, right? Where you have some sort of granularity of this. But again, in HBase, it's on a row. And it means that if 2 people are modifying different rows, that they can do at the same time. That's not a problem at all, right? In HBase. Well, in MongoDB, the granularity, it's a bit similar. It's a document. It means that 2 users cannot modify the same document at the same time. but they can modify different documents at the same time in the same collection. That's totally fine, right? So this is what it means. That's called atomicity. It's the granularity of atomicity. In PostgreSQL, you can actually get that at the level of multiple tables. It's very, very impressive. But MongoDB doesn't offer that. It only offers that at the level of the documents. Okay. All right. It's good because the fact that it's a bit slow slows me down. So it gives you also room to digest what I'm telling you. Now, next week or maybe the next hour, next lecture, I'm going to show you that we do have languages on the level of SQL that are a bit easier to learn and allow you to query collections of trees. We're going to focus on JSONic. It's largely based on a W3C standard, so standardized by several companies, probably 20 years of work now, the underlying standard called XQuery. XQuery is right there. GraphQL became popular a while ago. It's about specifying in JSON in your API a way to project and select some data. Uncle was also popular at some time. Nickel, NYQL, so Nickel was also is also one, and there's actually many others. These kind of languages. Okay, so we'll study, you'll see what they look like. Again, if you learn one, you will get the spirit and you can learn any other of these languages. Sadly, it's not like tables where you just have SQL and nobody disputes it. In trees, it has not converged yet. So we do have that unknown of where will we be in 10 years or 20 years. Will there be a unique language everybody uses? We'll see. But today we are not there yet. Okay. So now the architecture. So now I'm going to tell you two things that should not surprise you. It's that this collection of trees, we're going to do two things. We will replicate it and we will shard it. Who is not surprised? Very good. We've done that before, right? We did it in HDFS. We also cut into blocks the files. We also replicate them. So, you know, we do that all over the place, really, the sharding and the replication. Okay, so we have multiple copies of the collection of trees. I just, instead of putting a tree, I put a document image, right? Just plenty of documents. Document is the same as tree, right? Just to be clear, JSON documents, a JSON tree, it's the same thing. All right, so we have multiple copies, and on top of that, we are going to cut it into partitions. You can call them shards, chunks, blocks, splits, partitions. In MongoDB, we call them replica sets. All right, so for example, you could have some key and you look alphabetically, A to E is in the first shard and F to P is in the second shard and Q to Z is in the third shard, or I could say in the first replica set, second replica set, third replica set, and that's it. So you see, replication vertically and sharding horizontally. Who sees that? Okay. Now, if you look at machines, this is what it looks like. Now, that should be a surprise because that doesn't exactly look like what we've seen before, because in the case of HDFS and HBase and MapReduce, at least the version 1 and Yarn, we had a centralized architecture with a coordinator node at the top and plenty of worker nodes otherwise. But in the case of MongoDB, it's a slightly different architecture because we are going to be a centralized architecture, but in every replica set. So it means that we have a first shard, a second shard, a third shard, and in every one of these shards, we have a coordinator node and we have worker nodes. The number of worker nodes is not going to be in the thousands, like you could have with otherwise with HDFS and so on, right? For example, you might have just three, like one primary node and two secondary nodes in every shard, right? So the number of, of course, it's making progress with time, but most of the people using MongoDB, the number of machines they use is not in the thousands. It's more like in the counting on one hand, maybe a few dozens. Most of the people don't scale more than that. Okay, but it does allow you to replicate the data on multiple machines. So if one of them crashes, then that's fine. Plus, since you have multiple shards, you can also process the data in parallel across the shards. Who sees these two things? That with this, if it crashes, we don't lose data, and we can process in parallel. Who sees that here? Okay. Now, another thing, so here I show you a replica set with 5 worker nodes instead of just 2. The reason I put a bit more is that I want to tell you that when you write something, you add something to the collection, you delete something, it's going to make you wait a little bit until it has confirmed that a minimum number of machines have implemented your change, your update, deletion, insertion, and so on. In that case, we assume 3 of them, the primary and 2 of the worker nodes. And maybe the other 3 that don't have the tick, they didn't do it yet. But nevertheless, we consider that 3 is an acceptable quorum, an acceptable number. And now we are going to confirm to the user that this is done. And the propagation to the other 3 machines will just happen in the background, but without the user waiting. For who is that clear? Right? The first part is called synchronous. We wait until the first 3 confirm. And then asynchronously in the background, we propagate to the rest. 3 is something you can change. If you don't like 3, you can make it 2, you can make it 1, you can make it 6 if you really want to make sure that it's everywhere. This is something you control, right? Okay. Everything with me? Okay. Now I'm going to talk about indices. But in fact, who visited information systems for engineers? Okay, that will not be new to you. That's the good news. But I want to make sure that even if you didn't, then you know what an index is with MongoDB. And this would work in a very similar way for a PostgreSQL or a relational database. Indices are a trick on the physical level to make queries faster. It's the same query, it's just magically faster. Now, even if you don't know indices from PostgreSQL or from information systems, I'm sure you've all seen an index at the end of a book. Who has ever seen an alphabetical list of words at the end of a book with the pages? That is an index. And it works exactly the same way. And you probably see that the fact that you have this alphabetical list at the end of the book facilitates the lookup of a word, right? You immediately find the page and then go to the page. It's much faster than reading the whole book and looking for a word, right? So indices work exactly in that way. It's an additional structure that accelerates the queries. And the reason is we might have a very big collection, billions of objects, right? We might have a query that we call a point query because it looks for a very specific person, like name Euler is going to pick one of them, right? These are the ones we can accelerate massively. Then you might have queries that are not very highly filtering, like looking for mathematicians. There's going to be more than one, but it's also probably not the entire collection. So this would be, it would not be a point query in that case. Then we have range queries. If my computer would be so kind as to display the next slide, please. Yes, thank you. Range queries, this is the GTE I told you about. In SQL, it would be the greater than, like year greater or equal to 1918. That's a range query, and you see I put in bold and in blue everything that is higher than 1900. This is called the range query. This is the kind of queries we would like to make faster thanks to an index, if we build an index. So how can we make this super fast? Well, I'm going to show you. It looks a bit like this. Imagine that we had fruits in our collection and they contain colors. The idea is that on the left, you add some structure with a list of colors sorted in a certain way, could be alphabetically, could be by wavelength, since we are talking about colors. But basically, we have this sorted list of values, and then we have the pointers, these little arrows that point to the documents corresponding to the colors. It was built with this, right? We used that in order to build that structure. Now you see that if somebody specifically looks for orange, then you will follow the arrow. Orange you can find efficiently. It's like looking up in a dictionary, right? If it's sorted in a certain way, you look in a dictionary, and then you follow the pointer and find the documents that has the color orange. It might be that there's 10 or 100 of them, but then you will instantly see them because you just see the pointers that come from orange. So that's the general idea, right? I'm going to get more into the details. So here's an example. Now I'm dropping the colors. Imagine that we have a collection of scientists. I put 6 of them. We have their names. You see, it's a bit heterogeneous, like Albert Einstein is a bit different. A country and then a century. The country is, it is everywhere and the century is everywhere, right? Now I want to index on century. And that I can do with a command in my MongoDB shell. I can say create index, and I'm going to create a hash index on century. What is a hash index? You will know after the break, because it's actually 9 a.m. So after the break, I'm just going to finish showing you the index. It's the last topic for document store, so I'm going to finish the indices. Indices is the plural of index. And then we'll look at JSONic, which is the final the final lecture with material. So thank you very much and see you in 15 minutes.